In organic chemistry, traditional reactions usually require hazardous liquid solvents to force molecules to interact. Today, we are exploring a classic synthesis protocol that completely eliminates liquid solvents from the equation. This whiteboard is our blueprint. On the left, starting materials, anthracene and maleic anhydride. On the right, our goal, the complex product 9,10-dihydroanthracene 9,10-alpha-beta-succinic anhydride. The necessary hardware is listed below: a mortar and pestle, round bottom flask, air condenser, and a heating mantle. Because we aren't dissolving these powders in a liquid to mix them, we have to force the molecules together using strict mechanical and thermal manipulation. Step 1 is preparation. We begin by bleeding into a mortar. As long as these chemicals remain locked inside their large, separate solid crystals, they cannot interact. The reaction is physically blocked. Without a solvent to dissolve the barriers, we overcome this by aggressively grinding the two distinct powders together with the pestle. The mechanical force shatters the larger structures. This drastically increases the exposed surface area of both chemicals. By forcing these now microscopic particles to pack tightly against one another, their edges overlap. The molecules can finally physically touch, initiating the reaction. You know this step is complete when the two distinct powders become entirely indistinguishable, leaving behind a single, visually uniform fine powder. In a solvent-free setup, brute mechanical force substitutes for chemical dissolution. With the powders fully integrated, the mixture is carefully transferred into a round bottom flask. Heating this specific mixture introduces a major risk. Maleic anhydride is highly susceptible to sublimation. Sublimation means the chemical turns directly from a solid into a gas when heated. If left unchecked, the maleic anhydride will vaporize and escape the flask before it ever bonds with the anthracene. To prevent this loss, an air condenser is attached tightly vertically to the neck of the round bottom flask. This hollow glass tube acts like a chimney. As heat is applied, the hot vapors shoot upward and enter the condenser, but their momentum quickly starts to fade. The cooler ambient air surrounding the glass tube strips heat from the vapors inside. They condense into droplets along the inner walls and fall straight back down into the reaction zone. The air condenser creates a closed-loop thermal security system, trapping the volatile chemicals together until the synthesis is complete. Now the assembled round bottom flask is seated snugly into the heating mantle and the heat is activated. Looking back at our original whiteboard blueprint, you can see the small delta symbol resting above the reaction arrow. This indicates that heat is the primary catalyst driving this equation forward. Watch closely for the first phase change. As the temperature climbs, the dry powder suddenly melts into a dark, bubbling liquid. It is within this temporary liquid melt that the actual Diels-Alder molecular bonds are rapidly forming. Then, a counterintuitive second phase change happens. Even with continuous, intense heat applied from the mantle, the bubbling liquid abruptly freezes into a new solid mass. This rapid resolidification proves the reaction is complete. The newly synthesized product has a significantly higher melting point than the raw ingredients, which forces it to freeze in place even under heat. At this point, the flask is safely lifted out of the heating mantle and left to slowly cool down to room temperature. What remains inside is the crude product, a distinct off-white crystalline solid, caked tightly to the bottom of the glass. This solid mass confirms we have successfully synthesized 9.10-dihydroanthracene 9.10-alpha-beta-succinic anhydride, completing the exact blueprint from our whiteboard. To prepare this material for practical laboratory use, the next steps are to purify the crude mass through recrystallization and then run a melting point analysis to verify its absolute purity. By perfectly manipulating mechanical surface area and deploying a simple thermal vapor trap, complex organic syntheses can be executed without the environmental toll of traditional liquid solvents.